In the last video, we talked about how to construct the real numbers, the actual numbers that make up the real numbers. But we left out a few important details about real numbers, specifically arithmetic and order. In this video, we're going to talk about arithmetic, which means defining addition and multiplication in the real numbers. So first we're going to look back at some issues that we had with the rational numbers. You may not have worried about those issues, but they are issues that we had to worry about back then. Then we're going to use those experiences to see how they can help us add two numbers in the real numbers. So to define addition and multiplication in the rational numbers, first of all, we assume that we already had addition and multiplication in the integers. So for addition, for instance, what we did was when we had two fractions that represented rational numbers, a over b and c over d, and we wanted to add them, we had a certain rule for doing that, right? We found a common denominator and then added the numerators accordingly. So we got AD plus BC over BD, right? And that looks fine. It looks like a perfectly well-defined addition. The problem is it can work differently depending on what the representations of those individual numbers are. So if I'm adding 1/2 plus 1/3 and use that formula, I get 3 plus 2 over 6, which is 5/6. But if I say 2/4 instead of 1/2 and 4/12 instead of 1/3, I get a different looking number, 40 over 48. Now those two fractions represent the same rational number, but if I want to prove that generally addition has to be well defined for all ways that I can do that, I've got to prove that they're equivalent for all the ways that I can add two numbers together. So the big question is, how do we know we always get the same answer? Well, I'm not going to tell you what the answer is for rational numbers, but we will worry about that for real numbers. So for real numbers, we got to ask ourselves, how do we add two Cauchy sequences? And we'll do it in a very natural way, right? So if I have the Cauchy sequence A1, A2, A3, etc., and I want to add that to the Cauchy sequence B1, B2, B3, we'll just add them term by term, right? A1 plus B1, A2 plus B2, A3 plus B3. That's going to be our new our new number when we add those together, right? So the question you might ask is, do we have the same ambiguities as we did with addition in Q? And you know, of course, the answer to that is yes. And let's see how when we add 2 plus 3. Now, when we add 2 plus 3, the representatives for our equivalence class are I'm just going to say are the constant sequences 2, 2, 2, 2, 2, etc., and 3, 3, 3, 3, 3, etc. Those both represent 2 and 3 respectively. And so when we add those together, we should get 2 plus 3 as each of the terms, and that gives us the constant sequence 5. Right? And of course, we get all of its related Cauchy sequences, because again, those square brackets on the outside, we are talking about an equivalence class. So that has an infinite number of Cauchy sequences in that set. So the question is, what if we chose a different Cauchy sequence that represent 2, 2, 2, the number 2? And you know what? I'm not even going to tell you what the numbers are. I'm just going to tell you that's a random Cauchy sequence that I chose that represents the number 2. And another one, B1, B2, B3, that represents the number 3. How do I know when I add those together that I don't get a different answer? Well, we got to check it out. Will we still get the same equivalence class when we add those two together? So let me see. So I'm going to add A1, A2, A3, etc. to B1, B2, B3, etc. And we're going to use the same rule. I mean, it's not like we're going to do addition any differently. But we get A1 plus B1, A2 plus B2, A3 plus B3. And that looks very different than the constant sequence 5, 5, 5, 5, 5, etc. Right? But we got to prove that it represents the same real number. So we need to prove that the sequence that we get with A1 plus B1, A2 plus B2, etc. is the same one we get with the constant sequence with 5s. How do we do that? Well, we use our equivalence relation. So we know that AN is equivalent to 2 right? That's what it means for them to be in the same equivalence class. And that means that the sequence an minus 2 converges to 0. Bn is equivalent to 3, and that says that the sequence Bn minus 3 also converges to 0. See, so we know something about those Ans and Bns. They weren't just random Cauchy sequences that we picked up off the street. What we want is when we have the sequence An plus Bn, that is equivalent to 5. And so we know what we want. We know what the tilde means. So that really means that we want to prove that An plus Bn minus 5 converges to 0. And we're doing this from the definition. So we want the absolute value of An plus Bn minus 5 to be less than epsilon, where epsilon is some number that is greater than 0. Now, we want to somehow get 2 and 3 involved, because again, we know something about An and 2, we know something about Bn and 3, and the way we're going to do it is say, hey, look, I know 5 is 2 plus 3, and we have a negative 5 in that absolute value, so I'm going to use the fact that negative 5 is equal to negative 2 minus 3. So we plug that back in, we get An plus Bn minus 2 minus 3, we shift those terms around a little bit, we get An minus 2 plus Bn minus 3, and those look a lot like those An minus 2 and Bn minus 3 in the first couple lines up there. And we have the plus in between them, so you better believe we're going to use that triangle inequality. So when we use the triangle inequality, we get the absolute value of An minus 2 plus the absolute value of Bn minus 3. We know we can make An minus 2 the absolute value less than any positive number we want, same with Bn minus 3. So we're going to play that epsilon over 2 game with them to get things to work out. So we just need to make each of the absolute value of An minus 2 and the absolute value of Bn minus 3 less than epsilon over 2. So here's our theorem. We pretty much got the proof figured out. Our theorem is if the A1, A2, A3 gives us the same equivalence class as 2, 2, 2, 2, 2, and similarly with the Bn's and 3, 3, 3, 3, then A1 plus B1, A2 plus B2, A plus 3 plus B3 gives us the same equivalence class as the constant sequence with 5s. So by our assumptions about An and Bn, we know that An minus 2 converges to 0, Bn minus 3 converges to 0. We're just using the definition of our equivalence relation. So now we're going to let epsilon be greater than 0. Since epsilon over 2 is greater than 0, there exists some natural number n1 such that for all little n bigger than n1, we have An minus 2 minus 0, absolute value less than epsilon over 2. Similarly, there's an n2 such that for all little n bigger than n2, we have the absolute value of Bn minus 3 minus 0 less than epsilon over 2. And then we're just going to let big N be the max of n1 and n2. Then for all little n bigger than n, we have both absolute value of An minus 2 less than epsilon over 2 and the absolute value of Bn minus 3 less than epsilon over 2. And now we're going to do all of our nice little triangle inequality computations. Absolute value of An plus Bn minus 5 is absolute value of An minus 2 plus Bn minus 3. We use our triangle inequality to get that less than or equal to absolute value of An minus 2 plus the absolute value of Bn minus 3. But from above that, we have that is less than epsilon over 2 plus epsilon over 2, which equals epsilon. That gives us our proof. So here is our process of defining addition and multiplication. First of all, we're going to figure out how to add and multiply Cauchy sequences to create another Cauchy sequence. We're going to verify that using these rules on the equivalence classes doesn't lead to any contradiction. So there is no way for you to choose two different representatives of an equivalence class and somehow do the addition or multiplication and end up in different equivalence classes for your result. In other words, we're going to have to prove that addition and multiplication are what are called well-defined. And if that's a familiar phrase, you might have been in Math 350. So if you weren't in Math 350, don't stress out. We'll talk about this in class. But if you were in Math 350, you did come up with the concept of well-defined for arithmetic. And this is generally the same concept. So what's going to happen is we're going to work on this in class as well, but in the activities and the portfolio problems, one of the portfolio problems, you're going to go through this process for addition and multiplication, proving that they are well-defined. And now you're ready to work on those activities, arithmetic operations, and you just go ahead and click at the link below this video.